Section 15.3 2 and 3-dimensional boxes. The time-independent Schrodinger equation for a two-dimensional particle in the box is this. On the left-hand side, you have kinetic energy in the x direction and the kinetic energy in the y direction. The potential energy is 0. On the right-hand side, you have E psi. So essentially, you are looking at H psi is equal to E psi. The position and momentum of the particle in the x direction are independent of the position and momentum of the same particle in the y direction. We can separate x from y by setting this wave function of x and y to be a product of a function of x and a function of y. The function of x is uppercase x. The function of y is uppercase y. So we replace this Schrodinger equation over here, this psi with x times y, and this psi with x times y. So we get this equation. Again, this equation is simply H psi equals E psi. Psi is x times y. H is the sum of the kinetic energy in the x direction and the kinetic energy in the y direction. So now we apply this second derivative operator to the wave function, the product of x, y, here and here. Now remember, this y is independent of this x, and this x is independent of this y. So in this case, we can take the function y out of the second derivative with respect to the position x. Also, over here, we can take this function x out of the second derivative with respect to the position y. So we got this equation. Okay? Again, we are assuming x does not depend on y, and y does not depend on x. After looking at this reaction, we realize that it's possible to separate x from y by dividing both sides by the wave function psi. And psi is x times y. So we're going to divide both sides by x times y. We got this equation. Okay? And then we can move this part to the right-hand side. Now we get this equation. Okay? It looks very complicated, but it's really easy to solve because the left-hand side is a function of variable x and x only. The right-hand side is a function of y and y only. So essentially, we are looking at an equation that says a function of x and x only is equal to a function of y and y only. X and y are variables. They are independent of each other. How can you have this kind of equation? The only possibility is the function on the left-hand side is a constant. The function on the right-hand side is the same constant. So we're going to define that constant to be c over here, and then we can solve this equation easily, and this equation looks like a time-independent Schrodinger equation for a one-dimensional particle, and it is. And the physical meaning of this c is simply the energy of the particle in the x direction. So we simplified this Schrodinger equation for two variables, x and y, in 2 dimensions to this very simple one-dimensional Schrodinger equation. The c is simply the kinetic energy or total energy of the particle in the x direction. Well, another way to look at this is if you look at this equation, again, this is a function of x, this is a function of y. So you can also just take the first derivative of the left-hand side with respect to y, you'll get 0, right? Because this function does not depend on y, so the derivative of this function is 0. And also, this part is equal to this part. So this part on the right-hand side, its first derivative with respect to y should also be 0. That means this is independent of y. All right? So anyway, we're just trying to prove that both are constants if a function of x is equal to another function of y, and x and y are independent variables. This is the only possibility here. They should be both equal to the same constant. Well, again, we know how to solve this equation. This is just one-dimensional time-independent Schrodinger equation for a free particle. The solution is this. We solved this before. The energy is this. But now we have two dimensions. So I'm using n sub x for the quantum number in the x direction. Again, n sub x is the quantum number in the x direction. And a is the dimension of the x direction. So right here. Similarly, we have function for y. It's the square root of 2 over b, the normalization factor, times the sine function of ny times pi times y over b. Ny is the quantum number in the y direction. Nx and ny can be different from each other. A and b can also be different from each other. So the wave function of x and y is the product of this uppercase x and uppercase y. So it's over here. What about the total energy? The total energy is Ex plus Ey. Remember, energy is additive. Do not multiply an energy by another energy. That does not make sense. We are adding up the energy in the x direction and that in the y direction. So it's over here. They have a common factor, h squared over 2m, and then we have this two together in the parentheses. This is fairly simple. We can even further simplify these two equations if the particle is confined in a square rather than a rectangle. If it's a square, then a is equal to b. And then we can simplify the wave function. In the wave function, I just replace b with a. So this is the wave function. But again, nx can be and is often different from ny. Okay, so nx and ny are the quantum numbers in the x and y direction. They can be different. They are often different. In case they are the same, if nx is equal to ny equals 1, this is the ground state. That means the lowest energy state of the particle. The wave function looks like this. There's no node inside this square. The wave function reaches maximum when x is 1/2 of a and y is 1/2 of a, right here. Okay, this is just the two-dimensional projection of this three-dimensional picture. The vertical axis, actually it's not z, it's the wave function. The vertical axis is the wave function psi of x and y. Over here, this is x over a, this is y over a. So this is from 0 to a for x, this is 0 to a for y. Again, this is just a two-dimensional square. You are looking at a three-dimensional picture because the third dimension is the wave function psi of x and y. If nx is equal to ny is equal to 2, well, we'll be able to observe one node in the x direction and one node in the y direction. So this is how this looks like. Again, it's a product of two sine functions. So in this region, okay, you can see x is less than 1/2 of a, y is also less than 1/2 of a. So the two sine functions, one of x, the other of y, are both positive. So that's why the wave function is positive. Over here, actually both sine functions are negative, but the product is positive. So in here, sine function of x is negative, the sine function of y is positive. All right, over there, well, you have a negative sine function of y, but you have positive sine function x, therefore you have negative. And whenever you have a continuous wave function, if you go from positive to negative, there's going to be a 0 point in the middle, okay? Going from positive to negative, there has to be a 0 point in the middle. So we know there's a nodal surface here, and you can clearly see the two nodes. One here, this is x is equal to 1/2 of a. This line is y equals 1/2 of a. Again, when the box is square, we have a equals b, so the total energy is h squared over 8ma squared times nx squared plus ny squared. Again, nx and ny are the quantum numbers in the x and y directions. So what's the ground state? When nx is equal to ny equals 1, we have the lowest possible energy. It's also called a 0 point energy. So in quantum mechanics, the lowest possible energy is also called the 0 point energy. All right, over here, this is the energy. It's 1 squared plus 1 squared on top, and then multiplied by h squared over 8ma squared. What about the first excited state? Now we can have nx equals 1, ny equals 2, or nx can be 2, ny is 1, and then we have the same energy. In this case, we say we have two degenerate energy levels. One is this, one is this. They have different wave functions, different shapes, but since these two states have the same energy, the degeneracy is 2. Now we're looking at the first few energy levels. The first energy level, the second and third energy level are degenerate. So this one, this 2, are degenerate with a degeneracy of 2. So and then this nx can be 2, ny can be 2. 2 squared plus 2 squared is 8. Or you can have 1 squared plus 3 squared. That's 10. And then 2 squared plus 3 squared, that's 13. And then we have 1 squared, 4 squared, that's 17. So anyway, be sure that you use positive integers only. Okay, nx and ny cannot be 0. Now let's look at the three-dimensional case. This is the Schrödinger equation for the three-dimensional particle. On the left-hand side, you have h psi. On the right-hand side is e psi. So again, this is h psi equals E psi. H is the total energy operator, but because the potential energy is 0, we are looking at the kinetic energy in the x, y, and z directions. And now we try to separate the variables. Again, we set this psi to be a function of x times a function of y times a function of z. Well, the physical meaning is this: the motion, the position of the particle in the x direction is independent of those in the y or z directions. And now we replace this psi in the Schrödinger equation with the product of x, y, and z, and then we solve this equation. How do we do that? Again, we just need to divide both sides by psi, or the product of x, y, z. We get this equation, all right? And then we can separate the variables like we did before. We can move these two terms to the right-hand side. And then on the left-hand side, you see a function of x and x only. On the right-hand side, you see a function of y and z only. So left-hand side, it does depend on x. Right-hand side, it does not depend on x. So it has to be a constant. And that constant is simply the energy of the particle in the x, y, and z directions. The total energy is E sub x plus E sub y plus E sub z. And the total wave function is simply the product of this uppercase x, y, and z. So you have the product of three sine functions. Again, the dimensions of this box is a, b, and c. All right, the quantum numbers are nx, ny, and z in the 3 dimensions. What about the energy? The energy is just the sum of the kinetic energies in the 3 dimensions. They share a common factor, h squared over h squared over 8m. And again, nx, ny, and nz can be different from each other, and they are often different from each other. Again, this is because the motions in the 3 directions are independent of each other. Now, what if A is equal to B and B is equal to C, we are looking at a cube. And then the total energy is this, because A equals B equals C. Again, we're observe the degeneracy. So the lowest possible energy is obtained when nx equals ny equals z equals 1. So this will give us the lowest possible energy. It's actually 3h squared over 8ma squared, because we're looking at 1 squared plus 1 squared plus 1 squared. That's 3. So what about the second lowest energy level? Well, it's going to be 211 or 121 or 112. Which quantum number is 2? We don't care. Any one of the 3 can be 2. So we have a degeneracy of 3. So these 3 different states have exactly same energy. Now, what about the some other excited states? The next 3 excited states. Well, it's going to be 1, 2, 2, 2, 1, 2, 2, 2, 1. You need to square all 3 numbers and take the sum. So 2 squared plus 2 squared plus 1 squared is 9. The next 3 energy levels, 1 squared plus 1 squared plus 3 squared is 11. So the energy is 11 h squared over 8 ma squared. Now over here you have 12 h squared over 8 ma squared.